Thank you, Jan, for the introduction, and thanks to the organizers for the invitation to speak and for recording all the lectures. I'm looking forward to watching them later, as I said before. So everything I'm going to say today is joint work with Anton Besser and Stefan Müller. This talks about a new definition of P-adic adelic metrics and an associated definition of P-adic heights with the view towards giving a new explanation for quadratic Chaberty. So I think there have been several talks already at this conference the last 2 weeks, but the quadratic Chaberty method is a method in general for finding the rational points on a nice genus G curve inside the set of P-adic points in the realm where classical Chaberty method doesn't work. So the classical Chaberty method is a P-adic method for finding the rational points inside the set of P-adic points in the low rank setting, where the rank is less than the genus, which is the case generically. Most curves over Q tend to have low rank, but many interesting curves in nature, like modular curves, tend to have high rank. And the quadratic Chaberty method in the simplest setting is built to work in the case where the rank of the curve equals the genus, plus you assume you have some additional geometric input. And in this case, the method gives you certain analytic functions, P-adic analytic functions on the QP points, and you tend to find the rational points inside in certain level sets for this analytic function, right? So there are finitely many values that this analytic function takes on the set of rational points. So I'm sure this come up in other talks before, but let me mention this again. The first instance of the quadratic Chaberty method was built for finding integral points on odd degree hyperelliptic curves. This is the first example that showed like P-adic heights might give you a new method for coming up with such rational functions when the rank equals the genus. And this was like first built over Q by Balakrishnan, Besser, Müller, and later extended to all number fields by the same team together with Francesca Bianchi. And this method was then extended to work for all rational points by Nathan Dogram, Jennifer Balakrishnan, and their motivation came from the non-abelian Chaberty-Kim method. And in general, it works when the rank is less than the genus plus rank of the Néron-Severi of the Jacobian -1. So particularly if the rank equals the genus and the rank of the Néron-Severi, the Jacobian is larger than 1, you have a method for coming up with P-adic analytic functions that cut out the rational points. And the most spectacular application of this method was in recent times was like to find all rational points on this on the cursed modular curve, the last remaining curve in the classification modular curves with split Cartan level structure whose rational points we didn't know. And since then, there have been, due to Jan, Jen, Nathan, Stefan Müller, Jan Teutmann. Right? And since then, there have been many other examples. You can modify this to work for Atkin-Lehner quotients of modular curves and so on. I think there have been other talks on this at this conference. So let me give a brief outline of this method. I'm sure you've heard this before, but just to set up the framework once again, if I don't know if I can hide this. Okay. So in general, if you're trying to apply quadratic Chaberty to find rational points, again, like you have an auxiliary good prime of good reduction for your curve, and typically the functions that cut out these rational points tend to come from some kind of global function on the set of rational points on the Jacobian, right? So later on in the talk, we're going to interpret these global functions as certain P-adic heights associated to an extra line bundle on the Jacobian. But I'm just abstracting out the features that you need from such a function for running the quadratic Chaberty method. So you want a global kind of function in your head. You should be thinking of some kind of height function that comes with a local decomposition, a sum over all primes. These local functions are functions on the set of QQ points on the Jacobian. But it's not any old function, it's a function with some nice properties. You want this global function H to be a quadratic function on this abelian group J of Q, right? And the assumption that the rank equals the genus tells us that we have a particularly nice basis for the space of quadratic functions given by products of single integrals. So this global function, you can explicitly write, if you're trying to implement and express what this global function looks like, there's a nice basis in terms of products of single Coleman integrals and just basis of linear functions comes from integrating holomorphic differentials on the curve. And the global function H has a nice expression in terms of products of single Coleman integrals, and it naturally extends to a function on the set of PP points. The local function at P has a nice P-adic analytic nature. When we are specifically interested in restricting these functions to the set of rational points on the curve inside the Jacobian. So when you restrict the local height at P, local contribution at P, you get a certain iterated integral. These local functions have the shape, and the local heights. So the prime P is special here. So that's where this interesting analytic function comes from. But the primes away from P, you want these local functions to take on finitely many values when you restrict to the set of QQ points. And most of the time, you actually want them to be zero. So, for instance, when the curve has potential good reduction at Q, you want this local height to be identically zero. And in general, it's some kind of function that takes finitely many values on the set of QQ points. And if you look at this difference, so the analytic functions that cut out the rational points, they look like the global function H minus the local function HP. So we are going to look for the rational points inside the level sets for this analytic function. And when you restrict to the set of rational points in the curve, from this global decomposition of the height, this is exactly the sum of local heights away from P. And if you have the right kind of height function floating around, then this sum of local heights away from P will take on finitely many values. So in the quadratic Chaberty package, if you're trying to run quadratic Chaberty, you want a global function which has all these nice features. You want the global height to be a certain quadratic function. You want the local height at P to be, at least on the curve, to be given by an explicit iterative integral. And you want the heights away from P to take on finitely many values. And if you have all of these, you can find the rational points inside the level sets of H minus HP. And of course, you want to make sure that you don't write down a silly function. The functions that if the function that you write down happens to be identically zero, that's really not any constraint on the set of P-adic points. So you want to make sure that locally, this H minus HP on each residue disk, it's something non-constant, so it has finitely many zeros. So these two finiteness properties are key for cutting out a finite set of points inside the set of P-adic points on the curve. Right? So these are the features that show up in the kind of functions that show up for quadratic Chaberty. And in the previous talks, and hopefully in Jen's lecture series last week, you heard like you can build such a function if you have the additional data of a nice correspondence on a curve. And like modular curves tend to have very nice correspondences. You have the Hecker correspondence to work with. And you can produce such functions from these nice correspondences. So this was initially due to work of Jen and Nathan. And they were inspired by Chaberty Kim theory. So they used this data of an extra correspondence to build a particularly nice mixed extension of Hodge structures, and they use the fact that such extensions of Hodge structures have an associated p-adic height due to Nekovar. But in practice, when you need to describe these things explicitly, you need to make various objects in p-adic Hodge theory explicit. So you need to describe certain phi modules with like Frobenius and filtration and so on. So this is quite a difficult task in practice if you're trying to implement quadratic Cheverty. That's why like every time you have a specific modular curve, it takes quite a bit of work to describe all these functions quite explicitly in a way like you can plug into a computer. So our motivation when we started this project was to try and see if we could circumvent the use of any p-adic Hodge theory. So the initial data that's going into the quadratic Cheverty machine is rather geometric. It's this data of an extra line bundle on the Jacobian. And our goal was to try and see if we can directly explain why p-adic heights show up when you're trying to come up with rational points, with analytic functions that vanish on the rational points. So that's the kind of explanation that I'm hoping to give you today. Give you an explanation using tools from Markovitch theory to explain where analytic functions vanishing on rational points come from. So to be a bit more precise, what I'm going to do during this talk is to describe for you a new construction of a p-adic height, a canonical p-adic height associated to a line bundle on a Jacobian. And if you want to use this height function to run quadratic Cheverty, you want this global function. This is the h that we had before. We wanted to have all the nice features that I showed you 2 slides ago, and to have those features, you want a particularly nice type of line bundle. You want a line bundle whose class in the Néron-Severi of the Jacobian is non-trivial, but when you restrict it to the curve, it does pull back to the trivial bundle. Right? You can find such line bundles provided your Néron-Severi has sufficient rank. If Néron-Severi of the Jacobian has rank larger than 1, you can find a line bundle on the Jacobian whose restriction to the curve is has degree 0, but then you can twist it to make sure that it's actually trivial on the nose. So what I'm going to describe to you is a new construction of a canonical p-adic height, such that if you choose the right kind of line bundle, then all your conditions for running quadratic Cheverty are automatically satisfied, and they are a result of built-in features of this canonical p-adic height. And the whole goal was to describe a construction of this p-adic height that uses notions that are more familiar, like that appear in regular Aribam theory. So for describing this p-adic adelic metric, the key notion that we need is the notion of a curvature form associated to a line bundle. I will describe this in the next couple of slides. I describe how to build an adelic metric from a curvature form from this direct geometric information associated with the line bundle called the curvature form. It's a certain cohomology class that's associated to L. And once you have this adelic metric, you can build p-adic heights from p-adic adelic metrics. And if you pick the right kind of metric, so the canonical p-adic height, it will have the feature of being a quadratic function, which is one of the conditions that we wish for. And then it will follow directly from features from the theory of p-adic heights of line bundles, that if you choose the line bundle wisely, if you choose a line bundle that's non-trivial in Néron-Severi but pulls back to the trivial bundle, then all the conditions for running quadratic Cheverty are automatically satisfied. Right? So I just want to say, like you probably heard in the series of lectures, that there are many other constructions of p-adic heights already in the literature. Coleman-Gross height probably showed up a couple of times in in the lecture series, and probably also the Nekovar height, but like this older, there are also constructions due to Jarhan, Schneider, Mason-Tate, and so on. So you might ask, why build yet another theory of p-adic heights? There are a few nice features of this new construction. One thing is that these various constructions of p-adic heights, the previous constructions, they all felt a little different from the construction of real valued height. Narasimha heights, real valued heights for abelian varieties have been around for quite some time. So our goal was to build a theory of p-adic heights that very closely mimics the classical theory of Narasimha heights. So our definition, you will see, parallels construction of Zhang of Narasimha heights from heights from adelic metrics. Another nice feature is that it from the definition very naturally generalizes to times p of bad reduction for the curve. And initially, when quadratic Shepherd was first introduced, they had it was introduced for Q and for low degree number fields where you could verify a certain dimension hypotheses were true. So this framework very naturally extends. Very naturally works also over number fields. But to me, the most interesting feature of this new construction is it reveals this interesting connection between p-adic heights for different primes p. In some sense, some of the inputs for p-adic heights for different primes, quite a few of the inputs are the same. So I'll make this more precise again, like later on in the talk. But I think one thing that it does, it gives us a way to access classical Narasimha heights by a p-adic construction. So if computing Narasimha heights on the abelian varieties, like computationally is quite a difficult task, but this method, this new construction of p-adic heights, gives us a way to access contributions to the Narasimha height at finite places by computing p-adic integrals. Hopefully, I will get to this at the end of the talk. So this is roughly the outline to give you to describe for you a construction of p-adic adelic metrics and canonical p-adic heights, and then show how the nice features of p-adic heights that you need for quadratic Shepherd are automatically satisfied if you pick the right line one. Are there any questions, by the way? I don't know how this will work. I don't know if I can hear people in the room. It's a good place to pause.
Looks okay to me, but maybe I can ask a quick question. So the bad primes, do you have any restrictions on the reduction type of your curve? Does it need to be semi-stable?
No. No. You can work with, for computing these local contributions, you need descriptions of regular semi-stable models, but like there's no restriction on the reduction type. Q. Right. Okay. So let me first say what I mean by canonical height. So the classical Narasimha height is defined for abelian varieties defined over number fields together with the data of an additional line bundle. So you get a real valued function on the set of k-valued points on the abelian variety. What makes it canonical is how this height function interacts with the group law on the abelian variety. Right? So if you have a symmetric line bundle, so line bundle that's isomorphic to its pullback by -1, you want the height of n times p to be n squared times the height of p. Height of 2p is 4 times the height of p for a symmetric bundle. And for an anti-symmetric bundle, so where the pullback by -1 is isomorphic to the inverse, you want the associated height function to be linear. So this is what makes the canonical height canonical. It's how it behaves, how it interacts with the group law on the curve. So a p-adic height, a canonical p-adic height, it's essentially the same thing. Instead of a real valued function, now you have a QP valued function. But for building such a p-adic height, you need to make some auxiliary choices. You need the data of a continuous Adel class character, and you need this auxiliary data, this geometric input of a curvature form associated to the line bundle. I still haven't defined what it is, but it's a cohomology class that lives in omega-1 global differentials tensored with H1 derived of the abelian variety. Right. So if you have all this data, we have an abelian variety together with a line bundle and the extra data of a curvature form, you can build a canonical p-adic height. I said how I want the height function to behave. If you have a symmetric bundle or an anti-symmetric bundle, in general, you can decompose any line bundle into, or the square of a line bundle into a symmetric part and an anti-symmetric part, and you just add up the height. So in general, you're not going to get a pure quadratic form, you're going to get some kind of quadratic function. You look at the canonical height. Right. So let me describe the pieces for describing such a height function. It's a canonical height function is built from an adelic metric. So that's an adelic metric is a way of measuring sizes of sections at every place of your number field. So I need to describe metrics at each place of your number field. So I first describe the metrics away from P. So for this, this definition again, like this is already shows up in the literature. So more generally, you can take any nice variety over kV, replace V not dividing P. A metric on a line bundle on this abelian variety, a Q-valued metric is the data of a function on the total space of your line bundle, but minus the zero section. It's a Q-valued function on L cross, but it's a nice Q-valued function. It's locally constant for the analytic topology on L, and moreover, fiber. So this is naturally a GM torsor over your base X. So the fibers of L cross, they look like copies of K cross. And fiber by fiber, you want this to behave like the valuation at this place. So if you scale a section, scale of point in the fiber by a number alpha, then you want the metric, this function, to change by the valuation of alpha, right? And yeah, you want these heights metrics away from P to be Q-valued. There are natural Q-valued metrics that are around. For instance, metrics coming from integral models of your curve over OB, right? So these are certain intersection numbers. You spread out your line bundle to an integral model, and you do some kind of intersection theory. So you're going to get integers or in general rational numbers. There's also another nice class of metrics that are around that you get by evaluating on the trivial bundle. It corresponds to evaluating functions at your specified point and then taking the norm, right? So you have various Q-valued metrics, natural classes of Q-valued metrics around. So this is the data at places away from P in the adelic metric. The new ingredient is the local contribution at P, and for this you need the data of a curvature form associated to a line bundle. So what is a curvature form? Like I said before, it's a certain cohomology class that lives in global holomorphic differentials tensor H1 derived, but it's a cohomology class that's closely related to the Chern class of the line bundle. So there's the cup product map from omega-1 tensor H1 derived to H2. And the curvature form is a cohomology class that maps to the Chern class of the line bundle under the cup product pairing. So if you want a concrete example to keep in mind, you can look at the tangent bundle of a nice curve genus at least one. So usually when you describe Coleman-Gross height pairings, you have to make a choice. You have to split the Hodge filtration. You have to choose a subspace in H1, a complementary subspace in H1 derived to omega-1 to global holomorphic differentials. So the same sort of data that goes into describing a curvature form. So if you have an explicit basis for omega-1 with the dual basis in this complementary subspace, then a curvature form for the tangent bundle is this explicit homology class omega I tensor omega I dual. In general, the data of describing a curvature form is basically the same data splitting the Hodge filtration on the line bundle. You can build a curvature form for the Poincare bundle from the data of splitting a Hodge filtration, and from that you can build curvature forms for arbitrary line bundles on your abelian variety. So it's the same kind of auxiliary information that goes into the other constructions of p-adic heights in the literature. But we want to take this data of a curvature form and use it to build the local contribution at P to these height functions. So once again, these functions, they come from the local contribution at P is a certain kind of Coleman function on the total space of the line bundle minus the zero section. Not just on the abelian variety, but on this larger space. But now it's a nice analytic function. This is a p-adic manifold, and you're looking for a Coleman function on LV cross. And once again, you have a condition on how this behaves in the fiber. So these local contributions, we call them log functions because fiber by fiber, they behave like the p-adic logarithm. When you scale a vector in the fiber by a constant, the local function changes by the p-adic logarithm evaluated at this constant. And in applications, what we care about is describing these functions not on the whole space, but we want to describe them. Well, maybe X was bad choice of notation. Our base is going to be the abelian variety. We care about describing these local functions when they're restricted to the curve, when they're restricted to the p-adic points on the curve, and you have a very explicit formula that you can read off basically from the curvature form for this line bundle, right? So if the curvature form has the shape omega I tensor eta I, and you want to evaluate this log function as a function on the total space of a line bundle, but you want to interpret that, you want to pull back to the base of the curve and like interpret them as functions of the abelian variety. So if you want to evaluate it, say, you choose a section of this line bundle locally around some point. So that gives you, that maps the abelian variety back into LV cross. If you want to evaluate the log function composed with the section, further composed with the embedding of X into the abelian variety, then locally it has the shape, it's explicitly described by this iterated integral, and the terms, the differential forms that show up are directly related to the differential forms that show up in the curvature form for the line bundle. Almost, except you have to correct for the zeros and poles of the specific section that you've chosen. So there's a correction differential form that you can work out by solving a Riemann-Roch problem, looking for a differential form with prescribed zeros and poles. And this restriction basically looks like this iterated integral corrected by the integral of this differential form. You should think of this as some kind of correction form. At least from this description, it's clear that there isn't a unique definition of a log function associated to a curvature form. There is some flexibility in choosing this auxiliary differential form gamma, this correction form. The ambiguity is exactly this place of holomorphic differentials, the form of differentials with no zeros or poles, and this non-uniqueness is a crucial input that we exploit in the construction of the canonical p-adic height. So this log function associated to a curvature form, this local Coleman function on the total space of the line bundle is the ingredient at P for a p-adic adelic metric. So you can put all of this together. You can package these metrics at various places into a nice height function. So a p-adic adelic metric, okay, just repeat what I just said. You can define this for arbitrary projective varieties, provided you have curvature forms for your line bundle. And the Abelian varieties all have curvature forms. It's for any line bundle. So it's the data of a collection of metrics, one at each place. So for places away from P, you want to choose these nice Q-valued metrics or valuations. So fiber by fiber, you have a function that behaves like the p-adic valuation, and you want these log functions at places dividing P. And at almost every place, you want these local contributions, these valuations to be ones that come from integral. So once you have all of this data and you have the auxiliary choice of an adel class character, you can package all of this information together to build a p-adic height associated to this p-adic adelic metric. So just like the usual Laurent height, it's given as a sum of local contributions. So you pick your favorite point on your k point on your variety, and you choose a section of this line bundle above this point, and you can say it's a section that doesn't have zeros or poles. Then you can evaluate these local Q-valued valuations at places away from P. So these rational numbers. At the end, you want to build a p-adic number, so you scale these by the constant that you get by evaluating the class character at a uniformizer, at any uniformizer at P. And then at places away from P, at places dividing P, you evaluate the log function at the section. Right. So the global height is the sum of local contributions, and it's independent of the choice of section that you choose. In the classical Laurent height, the independence of choice of section comes from the product formula. Here, this comes from the fact that you choose. This comes from the fact that the adel class character vanishes on K cross. So choosing a different section, another section differs from the original one by scaling by a p-adic constant. And so if you this is normalized the right way, so that this when you change the section, the constants all like add up to 0 because the adel class character vanishes on K cross. So that's how you build a p-adic height from a p-adic adelic metric. And want to explain how you satisfy the conditions in your quadratic Chaberty wish list from features of this p-adic height. So just as a reminder, so what did we want for running quadratic Chaberty? We wanted this global height to be a quadratic function on the rational points on the Jacobian. At places away from P, you want the local height on the KV points to take on finitely many values, and you want the difference h minus hp. You want to make sure you've written down interesting functions. So locally in each residue disk, you want to make sure you've written down a non-constant function. You want the global height minus the local height at P, now viewed as a function of the p-adic points, to be non-constant in each residue disk. Right. So if you choose the right kind of line bundle and the right kind of p-adic height, each of these are satisfied. So if you want the global height to be a quadratic function, you want to construct an adelic metric, which is the canonical adelic metric. So it has the nice kind of scaling property when you scale a multiply point by P. So for the canonical p-adic adelic metric gives rise to p-adic height, which is a quadratic function. If you want the heights away from P to take on finitely many values, if you choose a line bundle that restricts to the trivial bundle on the curve, the corresponding p-adic height turns out to be turns out to be a particularly nice kind of metric. It's something called an admissible metric on the trivial bundle, and these metrics have the feature that that the metric factors through the reduction graph of the curve. It does not care about what the point actually is. It just cares about which component the point specializes to in an integral model. And if you want to make sure you've written down an interesting function, something that's not identically zero, you want something that's non-constant in each residue disk, provided you choose a line bundle that's non-zero in the neuron severity of the Jacobian, you can show by hand that these functions, h minus hp, are non-constant in each residue disk. So each of the hypotheses that you impose on L naturally satisfies each of the conditions in your wish list. So you are done. You can run quadratic geometry provided you know how to construct the canonical p-adic height associated to a line bundle. And let me very briefly describe to you how the construction works. And again, point out that this really just works for any variety and any line bundle over a number field, provided you have the data of a curvature form. So the way we build these canonical adelic metrics, we don't do this for each line bundle. It's enough to metrize the mother of all line bundles, the Poincare bundle on the Jacobian. And any line bundle on A is the pullback of the Poincare bundle, and like you can pull back the data of a metric on a line bundle. So it suffices to metrize the Poincare bundle. And the key for metrizing the Poincare bundle is the fact that log functions, these local functions at P, are not uniquely pinned down by the curvature form. And not just that, you know exactly how the ambiguity in pinning down these local functions, these log functions. Any two of them differ by the integral of a holomorphic form. So if you want to make a log function, an adelic metric that's canonical, one way of phrasing that is saying that is that you want this isomorphism of line bundles. Poincare bundle is a symmetric bundle, so the pullback by 2 is isomorphic to the 4th power. If you want to make this isomorphism in isometry, you first choose an arbitrary log function at P. Maybe the pullback by 2 and the pullback by 4 don't quite coincide, but you can change it. Maybe you have the wrong one, but you can try to fix it by adding the integral of a holomorphic form. You can see how the two sides of this isomorphism change. One changes by twice integral of omega, and the other side changes by 4 times and the integral of omega. So there's exactly one choice which makes the difference 0. There's a unique choice of metric, a unique choice of log function that makes this isomorphism in isometry. So that's how you pin down the canonical metric at places dividing P. And for now, just to describe a construction for places away from P, I'm going to cheat and use the contribution to the neuron-tate height at places away from P. So there is a canonical Q-valued valuation already floating around, one where this isomorphism is in isometry. That's the local contribution that shows up to the canonical neuron-tate height. So if you make this choice, these choices of canonical log functions and canonical valuations away from P, if you package them together, you get a canonical adelic metric on the Poincare bundle, and then by pullback to arbitrary line bundles on abelian varieties. So that's the construction of canonical p-adic adelic metric and p-adic height. Any questions so far?
No, I think everyone has a very contented look, so I think it's fine to carry on.
Okay, great. So the last couple of minutes, I want to tell you how I mean, this last step might have felt like cheating, like, I think I said at the beginning that computing canonical Néron-Tate heights is computationally quite a difficult problem. I think the only algorithms we have or at least for approximating Néron-Tate heights are for elliptic curves and for genus 2 curves, and maybe now for genus 3 curves, where you explicitly compare the Néron-Tate height to the standard height and try to get explicit error estimates. In general, it's quite a difficult problem to get your hands on the canonical Néron-Tate height. But I promise the new P-adic method for computing these guys. So that's what I want to describe. And this crucially needs the fact that there are methods, inputs for describing P-adic heights also work at primes of bad reduction. I think from the definition I showed you before, you see that locally for describing these P-adic heights, you need to be able to compute these P-adic integrals of differential forms. Turns out there's more than one way to integrate a differential form when your curve has bad reduction. So this is a summary of what different integration theories look like. So there's a natural extension of Coleman's integration theory, which I think Jen definitely mentioned in the lectures, like algorithms for computing Coleman integrals. It works really well when your curve X has good reduction. There are algorithms to compute Coleman integrals, but when your curve has bad reduction, the domains on which these Coleman integrals are defined, it's not the entire analytification of the curve. It's only defined on certain subdomains, on these so-called wide open subspaces inside your analytification. Whereas there's a better theory that's insensitive to the reduction type of a curve. That's it's called Vologodsky integration. And this naturally, if you interpret the integrals that show up in log p, in these log functions as Vologodsky integrals, then the whole framework of P-adic heights carries over. You can define these functions that vanish on rational points even when X has bad reduction. But in general, the type of integrals we know how to compute are these Coleman integrals. So we need some way of taking these computations of Coleman integrals on these subdomains in your analytification and tease out from it the Vologodsky integral, the integrals that show up in P-adic heights. So the slogan here is that Vologodsky integrals can be computed from Coleman integrals on these subdomains. So the structure of your analytification is that it can be glued together from these basic wide open subspaces, and the overlaps look like rigid analytic annuli. And on these, when you restrict your Vologodsky integral to these subdomains, it is given by a Coleman integral. But you might have possibly different Coleman integrals on these different subdomains, and you need some way of patching them together correctly. And the patching conditions come from a certain kind of harmonicity formula. So there's this recent comparison of iterated Coleman integrals with iterated Vologodsky integrals due to Eric Katz and Daniel Licht. This generalizes earlier work of Amnon Besser and Sarah Zervis for single integrals. And the slogan is that Vologodsky integrals are basically locally given by Coleman integrals, but you patch them along these gluing subdomains on annuli by using appropriate correction constants. It is a constant if you're talking about single integrals. The difference of Coleman integrals on the two sides of an annulus will be a constant. In general, you have transition matrices that describe the solutions to these P-adic differential equations on the two sides of an annulus, and these transition matrices obey some kind of harmonicity condition. And so in some sense, at least theory, we have a way of teasing out these Vologodsky integrals from local Coleman integrals. And the question is, okay, can we get a handle if all we wanted to do was compute iterated Coleman integrals, and say we're willing to do this at every place of our number field, can we use this to tease out the data we need at places away from P, right? So so notation is a bit confusing, but the goal is like now we want to understand P-adic heights for different primes. So there's a superscript L. This means we're looking at the QL valued height associated to a line bundle at L. And the question is the local contribution to the QL valued height at P in some way related to these P-adic integrals at P? And so is there a connection between P-adic heights, QL valued heights for different L? And in some sense, if all you wanted to do was take this take as input the data of this curvature form at each place of your line bundle, and if you're able to compute these iterated integrals that describe the local height at P, can you tease out the values of the local heights at P to the QL valued heights? And we have such an answer in our work. So turns out that these local heights at P, if you work out if you write out what these integrals look like, they depend on the choice of a P-adic logarithm. And if you don't want to choose a particular value, you can view these local log functions as a polynomial in the formal variable log P, a polynomial of degree at most 2. And it turns out if you study the dependence of these log functions on the choice of P-adic logarithm, you can, from it, you can extract these canonical valuations. So, so the precise statement is that if you take the local contribution at P to the canonical P-adic height, this canonical log function, then it's a polynomial in this formal variable log P. So you look at the coefficient of this polynomial of the leading term, the coefficient of log P in this polynomial. So one way to express that is take the derivative with respect to this formal variable log P and evaluate at log P equals 0. So this is the coefficient of the leading term. So this coefficient, this dependence on log P, behaves like a valuation. And it's not any old valuation. It is a Q value valuation that shows up in the contribution to the neuron weight height. So this is a way of unifying, relating the P-adic height to local contribution that shows up in the neuron weight height, and like in particular, the local contribution to P-adic heights at different primes. Right. So the dependence of the local contribution at P to the P-adic height can tell you at bad primes, for instance, prime of bad reduction, the dependence on log P can tell you, can give you this intersection theoretic data at places away from P. So I just point out an advantage of this. Again, it gives us a uniform way of computing the local contribution at all places, starting from just the differential data of a curvature form, provided you're able to compute these Vologodsky integrals. And it gives a new P-adic analytic way of getting contributions to the classical real valued neuron weight height. So in some way, it's a unification of the theory of height functions at all places. So this must say that one of the stumbling blocks in like explicitly doing quadratic Cheberty computations for a large class of curves is like getting your hands on the values of these local heights away from P. I think the initial applications, you looked at curves with potential good reduction at all places. So you only had, so the local contributions were automatically 0. But in general, it's a difficult task getting your hands on these finitely many values of the local heights away from P. But there is this, initially this like the work of Alex Betts and Eitan Dogra for formulas for computing these local heights. And again, carrying this out explicitly in examples, it involves describing the action of the correspondence on the dual graph of a semi-stable regular model, and knowing how correspondences act on the cohomology of individual curves in the reduction. So it's maybe not immediately obvious how to get your hands on this data directly from, say, differential data on the curve, but this approach using what we call Vologodsky valuations tells you how to tease out values of local heights just from computing these Vologodsky integrals that play this above. So this, I must say, there's also recent ongoing work. I think this was mentioned in Jen's talk, to implement this, carry out this local contribution, computation of the local contribution at places away from P using the formula that shows up in work of Alex and Nathan on a database of hyperelliptic curves by Alex Betts, Juanita Ruzero, Sachi Hashimoto, and Pim Spellier. And it takes as data, it takes as input the data of how the correspondence acts on the Durand cohomology of the curve. And we recover the same in this is work in progress, but we show that we can write down explicit formulas for these Vologodsky evaluations. Actually, you don't need to evaluate this Vologodsky integral all the way. You just need very minimal information about what these Vologodsky integrals look like to tease out the values of these Vologodsky evaluation. I think that's all I want to say. Thank you very much for your attention.
All right. Thank you very much, Padma. Are there any questions from the audience? Do you have a microphone?
Oh, yeah. Yes, thank you very much for your talk. I had at least one question. First, for a sanity check, what's going on when you take L that is actually 0 in the Neuron-Severely subgroup? What doesn't work at the end?
Oh, so what happens if L is 0 in the Narasimha? You just end up, I mean, H minus HP is identically 0. I mean, you don't get an interesting, the vanishing locus is all of QP. You don't have ways of showing that. Let me scroll all the way back to the wish list. You want to make sure that the functions that you write down are non-constant on each residue disk. That comes from the assumption that L is non-trivial in the Narasimha.
Okay, so it's really constant H minus HP when you're looking at something in the Narasimha, right? You get okay.
Yeah, at least you don't have a way of showing that you don't get the 0 function.
Okay. And then maybe another one if that's okay. What happens if you change the curvature form?
I mean, in the usual setup, it's the same thing as changing the splitting of the Hodge filtration in the Coleman-Gross height pairing. So I think you can the functions that you write down do change, but I think both the global height and the local height at P maybe change the same amount. So at the end, you don't pick up, you don't see any difference in the difference between the global height of P and local height of P. I mean, Jan and Nathan can correct me if I say something wrong. Changing the splitting of the Hodge filtration, I don't think it gives you new functions. I mean, I haven't really done this on examples myself, so people who have done these computations can correct me if I say something wrong.
Okay, thank you.
I have maybe also a question myself. So in your new height theory, you have the contributions away from P and the contributions at P. Of course, the most mysterious one is the one at P. So I was just wondering, in the case of a Mumford curve, so where you have totally degenerate reduction, and there's a uniformization by something like the upper half plane, is there any description of your contribution at P in terms of theta functions on the upper half plane? P-adic upper half plane.
I think Stefan has work, decent work. Like he wants to compute P-adic heights for various reasons, also for verifying things like the P-adic BST formula, I think. And I heard him give a talk this summer. I think he has work on computing these P-adic heights using P-adic sigma functions and theta functions for hyperelliptic curves, exactly the way you're describing.
Okay. Thanks.
I don't know if he's posted this yet. So there's Stefan, Elitskaya, Mark, Matthew, and maybe someone else I'm forgetting. But
I see. Yeah, thanks. Yeah, I think for the Schneider height, such a description is known by Werner, but for your height, I wasn't sure. Are there any other questions for Padma? No? If not, then let's thank her again.